Hello, and welcome to our review for AP Chemistry, Topic 5.2, Introduction to Rate Law. In this video, we'll be talking about a lot of stuff, so hope you're comfortable because there's a lot to discuss. First off, rate has to do with how fast a reaction goes as measured by the amount or the concentration of product that is produced and the rate that it is produced. In other words, the concentrations change over time. Or we can measure the rate by the disappearance of a reactant. So the disappearance of A in this particular reaction or the disappearance of B in this reaction. And again, rate always has to do with something over time. So we're talking about the appearance of C over time or the disappearance of A or B over time. That can be measured in a couple of different ways. It's not always easy to measure the rate of a reaction. You have to have something that you can actually measure. So if we had two colorless solutions producing a colorless solution, it could be a little difficult to measure the rate of the reaction. But if we had a colored solution, like one of these had a color to it, then we could measure how fast, if C had a color to it, how fast C appears, how the color changes over time, or how quickly, if A or B was colored, how quickly that color disappears over time. And we could use the Beer-Lambert law to measure those concentrations as those colors change over time. We could also measure how fast the pH changes. If this was an acid-base reaction, we could measure the change in pH. And by measuring the change in pH over time, we would be able to measure the rate of the reaction. We could also measure, if these were gases, in my example here, these are aqueous, but if these were gases, we could measure the change in pressure over time, because as one gas disappears, the pressure would decrease, or as a gas appears, the pressure would increase. And so we can measure the change in pressure of the system to measure the rate change over time. Also, if this was a reaction that produced ions in solution, we could measure the rate that those ions go into solution by measuring the conductivity. And so that's another way that we could measure it. Or if ions were precipitating out, we could measure how the conductivity decreases over time. So those are all different ways that we could measure the rate of this reaction. So what is the rate law? Well, the rate law expresses the rate of a reaction as proportional to the concentration of each reactant raised to a power. And so what the rate law looks like is it expresses the rate is equal to some proportionality constant called the rate constant, which is given the symbol lowercase k, times the concentration of our reactants. So the concentration of A, and remember brackets means molarity. So the concentration of A raised to some power. And that power is called the order, and it could be 0, 1, or 2 most of the time. It can be some other variations, but usually it's going to be 0, 1, or 2. And then times the concentration of our other reactant raised to some power, which also is called its order, which is either 0, 1, or 2. Again, those can be other numbers, but usually they're going to be 0 order, first order, or second order. So what does order mean? Well, it means how does the rate relate to the change in concentration of the substance A, and how does it relate to the change in concentration of substance B? So if M was 0, so it was 0 order with respect to A, that means anything to the 0 power is 1. That means the rate wouldn't change if you change the concentration of substance A in this chemical reaction. The reaction would go the same rate no matter what the concentration of A was. Same thing with B. If B was 0 order, then whatever the concentration of B is, the rate would stay identical if you change the concentration of B. What if it was first order? If it's first order, that means it's a direct relationship with the rate. So if you double the concentration of A, then you would double the rate of the reaction. If you doubled the concentration of B, then you would double the rate of the reaction. What if M was 2, so that this reaction was second order with respect to A? Well, what that would mean is that the rate is quadratically related to the concentration of A. So if we doubled the concentration of A, 2 squared would be 4. So the rate would quadruple. Same thing with B. If B had an order of 2, then if we doubled the concentration of B, that would quadruple the rate of the reaction. And so order tells us how the rate is related to the concentration of our reactants. The overall order of the reaction is simply the sum of the orders. So the sum of those exponents, so m plus n, gives us the overall order of the reaction. So if it was second order with respect to A and second order with respect to B, then 2 plus 2 is 4, so the reaction would be fourth order. If the reaction was first order with respect to A and second order with respect to B, 1 plus 2 would be 3, so the reaction would be third order. The order also affects what the units will be on your rate constant. So the rate constant has units, but those units change depending on the overall order of the reaction. So let's say that this reaction was second order with respect to M. I'm just going to put a little 2 up here to remind us of that. And first order with respect to B. So that means concentration squared, the unit for this would be molar squared times, and if this was first order, the concentration of B would be molar to the first power. And so molar to the second power times molar to the first power would be molar cubed. So if this is molar cubed for the units of our concentrations raised to their orders, K has to be some unit that will give us a rate unit of molar per second, because rate is change in concentration, change in molarity, over change in time, seconds. So molar per second. So what can we multiply molar cubed by that will give us molar per second on the left-hand side? So if you think about it, we need 2 molarities in the denominator times seconds in the denominator. And if you'll notice, molar squared in the denominator times molar cubed in the numerator will leave us with 1 molarity in the numerator. And molar times inverse seconds gives us molars per second. So we can figure out the units of K by looking at the overall order, and in the denominator having 1 molarity, 1 less than the overall order, times seconds. So that's a question that will pop up quite often on the AP test, so keep that in mind, is trying to figure out the units of K on the rate equation. So the rate law simply expresses how the rate is affected by the concentration of each of the substances, and those exponents are the order. Now, an important thing is notice that I did not use the coefficients as the exponents in the rate law. That's a very important thing to remember, that the orders are not necessarily related to the coefficients. They are different numbers. So our coefficient in front of A could be 2, but the order could be 1 or 0. It could also be 2, but it doesn't have to be 2. So these orders are not related to the exponents in an overall chemical equation. We'll talk more about that in another video. So another important thing about the rate constant is that it is temperature dependent. In other words, if we change the temperature that a reaction takes place at, then that's going to change the rate, and that will change the rate constant. The rate constant is temperature dependent and is only valid at a certain temperature. Again, if the temperature changes, then that's going to change the value of K. How do you get the value of K, and how do you get the value of these orders? Those have to be experimentally determined, and we're going to look at a method for doing that next in this video. So that is some basics about the rate law and the rate equation. Let's go ahead and look at a method for solving for the value of K as well as the orders for each individual reactant. So I'm going to scroll down to an example that I have here. And for some reason, I cannot scroll. So let me scroll the screen down to our example. So this method of solving a problem is called the method of initial rates. And what the method of initial rates entails is doing various experiments with different concentrations of your substances in the reaction and measuring the initial rate of formation. In other words, how quickly is the product produced? What's the rate of the product's production? And so our reaction that we're going to look at is nitrogen monoxide reacting with oxygen to produce nitrogen dioxide. And we're going to look at this data and try to figure out what is the order with respect to NO for this rate and what is the order with respect to O2 for this rate. So first I want to write the rate law for this equation. So we're going to write the rate law, which is rate is equal to K, the rate constant, times the concentration of NO raised to some power times the concentration of O2 raised to some power. Now, before I move on, I just want to point out, these are gases. We could also write the rate law in terms of pressures. Whenever you have a gas, the rate law is also proportional to the pressures of the gas. So you could be given pressure data for a gas and put pressures in here instead of concentrations. And that would be valid also. So just keep in mind that with gases, you could also do the rate equation with the rate law with pressures. So how are we going to solve this problem? Well, our goal is to figure out what is M, what is N, our orders, and what is K, what's the rate constant. So to solve this problem, we need to look at our data. So notice in experiment 1, the initial concentration of NO is 0.1 moles per liter. The initial concentration of oxygen is 0.1 moles per liter. And the experimentally determined rate of formation of NO2 is 2.5 times 10 to the negative 4 moles per liter per second, molarity per second. Now we're going to compare that to experiment 2, and this is where things are kind of cool. If you look at it, we've kept the concentration of oxygen constant. So since the concentration of oxygen is constant, that's not going to change the rate of the reaction. But we doubled the concentration of NO. And so we want to look, when we doubled the concentration of NO, what did that do to the initial rate? Well, if you look at what it did to the initial rate, 2.5 times 10 to the negative 4 became 5.0 times 10 to the negative 4. That doubled the rate of formation. So doubling the initial concentration doubled the rate of formation. So what does that mean? Well, that means that our M must be 1. Because if we double the concentration, we doubled the rate, and 2 to the first power is 2. So we doubled the rate. So M, looking at the data for experiment 1 and 2, M is equal to 1. Now you could do this mathematically by substituting in experiment 1's values into this equation and substituting experiment 2's values into these equations and do it mathematically. And let me show you what I mean. If we take 2.5 times 10 to the negative 4, that equals our rate constant times 0.1 to the M power times 0.1 to the N power. We're also going to substitute in the second experiment's values. 5.0 times 10 to the negative 4, 4, not 9, 4, equals the same proportionality constant, the same rate constant, times a different concentration for our nitrogen monoxide, but the same concentration of our oxygen. So now we have our two equations here. If we take these two equations and divide them by each other, and I'm going to actually divide the second equation by the first equation to make the math a little nicer. So I'm going to divide the second experiment by the first experiment. Watch what happens. This is where things are kind of neat mathematically. The 0.1 to the N power cancels because it's in the top and bottom. The K cancels because it's in the top and bottom. And 5 times 10 to the negative 4 divided by 2.5 times 10 to the negative 4 is 2. And that equals 0.2 to the M power divided by 0.1 to the M power is 2 to the M power. And so what is M? Solving for M, M must be 1. So that's how we can mathematically or algebraically solve for that order. But we can also logically see that when we doubled the concentration of NO and kept the concentration of oxygen constant, the rate doubled, so the order must be first order. We're going to do the exact same thing with the other substance, O2. Notice that experiment 1, experiment 2, the concentration of NO is 0.2, and in experiment 3, the concentration of NO is 0.2 also. So the concentration of NO stays constant. But O2, the value of the concentration was quadrupled. So we're going to do the algebra again for this reaction. So I'm going to substitute in the rate for experiment 3, 8.0 times 10 to the negative 3. That equals the rate constant times the concentration of NO, 0.2 to the m power, times the concentration of O, 0.4 to the n power. Then I'm going to divide that by 5.0 times 10 to the negative 3 equals the same rate constant, the same concentration of NO, and 0.1 to the n power. So we're going to divide this and watch what we get. If you do 8.0 times 10 to the negative 3 divided by, 10 to the negative 4. I apologize for that if that confused you. Sorry. That one's negative 3. This bottom one is negative 4. Sorry if that confused you. Okay. 8 times 10 to the negative 3 divided by 5 times 10 to the negative 4. That will give us 16. K's cancel out. 0.2 to the n power cancels out. And we get 0.4 divided by 0.1 to the n power, which is 4 to the n power. So 4 to what power will give us 16? 2. So when we quadrupled the concentration of O2, we multiplied the rate by 16. That means that the order with respect to O2 must be 2, because 4 squared is 16. So we just saw for the orders of this reaction, m is equal to 1, n is equal to 2. So we've now solved for those orders, and we can write our rate equation. Rate equals K times the concentration of NO to the first power times the concentration of O2 to the second power. And so this is called the method of initial rates, just solving for those orders by looking at which substance's concentration changed and how did it affect the rate. The last thing we can do is solve for K, and the way we can solve for K is simply substitute in one of our experiments. It doesn't matter which experiment, because this equation is true for all these experiments. Substitute in the data for one of the experiments and solve for K. So we'll just do experiment 1. The rate is 2.5 times 10 to the negative 4 equals K times the concentration of NO, 0.1 to the first power, times the concentration of O2, 0.1 to the second power. And so we want to just mathematically solve for this value of K. I'm going to do that real quick. So 0.1 times 0.1 to the squared divided by 2.5 times 10 to the negative 4. And that gives me a value of 4. So the rate constant is 4. It's unusual that you get a whole number like that. But in this case, they made the math a little easier. And so the rate constant is 4. So we would just substitute that into our final equation. So the rate equation or rate law for this reaction is 4. Now let's get the correct unit on K here. We have 3, a total order of 3. So the unit for K must be molarity to the negative 2, because it's the concentration's going to be the concentration is going to be 1 less than the overall order in the denominator, times seconds to the negative 1, so seconds in the denominator, times the concentration of NO to the first power times the concentration of O2 to the second power. And that is our rate equation for this reaction, or rate law for this particular reaction. Again, if you change the temperature, this value of K would be different because these initial rates of formation would change. So that's a basic introduction to the rate law. Hopefully that helped you out. I wish you the best of luck as you study for your exam. If you have any questions, please let me know. Bye-bye.